Right, so we're going to learn today about random decay and half-life. And half-life really does need to be explained in a bit of detail because while it's a very common natural pattern, this half-life pattern that we're going to look at, it's a little bit unexpected and a little bit counterintuitive. First thing we need to know is that decay is random. And there's two words that we use to describe this randomness. One of them is random, but the other is spontaneous. Now, what we mean by spontaneous and random is that we don't know when something is going to happen, and we don't know if there's several of something that could do a thing. We don't know which one of those some things are going to do that thing. So if we look at our radioactive nuclei, our unstable nuclei, let's say we have 5 unstable nuclei. The random nature is we don't know which one of those 5 is going to decay next and emit its radiation. It could be any one of these 5, and there's no way to tell. The other thing is the spontaneous thing is we don't know when they are going to decay, so we can't sort of predict when or if a particular nucleus is going to decay. So let's just have a quick example of this. We sit watching these 5 unstable nuclei and we wait 35 seconds and this one goes. That one's decayed. It's emitted its alpha particle or its beta particle or its gamma ray and has decayed. Now, we don't know which of the other 4 remaining ones are going to go next. We also don't know when they're going to go. So it might be 2 days before this one decides that it's going to emit its radiation and decay into something more stable. Okay, so then we wait, what was that, 2 days? Well, maybe we wait 14 seconds and this one decides to go. All right, and then literally half a second later, this one goes. And then a month later, the last one goes. No perceivable pattern to this. It is random. There is no sort of predictable way of telling which one is going to go off next and when that next one is going to happen. This does make radioactivity a little bit unpredictable. However, you rarely find 5 nuclei together. It's more likely to be billions of nuclei together in one sample. So thankfully, we've done so many experiments on this, we've seen patterns of how overall a material will behave over time. And this is a good model of that. This is an animation that repeats, so it's not truly random in that sense that it's the same every time, but the process is broadly what we'd expect to see with a radioactive sample. What we've got is 100 blue circles, and those blue circles decay randomly. And they decay in the same manner that we'd see a radioactive sample decay. So hopefully what you've seen for the 2 times that it's run so far, and you'll see on the next time, is that at the beginning, lots and lots of circles are turning red. They are decaying, they're emitting their radiation, becoming more stable. But as the process goes on, this decay slows down. So as there are fewer atoms, fewer unstable nuclei to turn red, they turn red less frequently. So this gives us this really nice half-life curve that I've drawn on the graph there. It's very characteristic of half-life. This is a more simplified, well, maybe not more simplified, this is a more idealised curve, I suppose. It's not got the lumps and bumps that the last curve had. This is what we'd see maybe if we did have 1 billion atoms instead of 100. And what you can see is on here, half-life is labelled 3 times. And the half-life is this amount of time. So about, what's that, 55 seconds? Something like that. So, and what this means is that basically we've started with 100% of our sample there. It's all radioactive, okay? When it gets to 50% just here, so when half of the radioactivity's gone away, 50% is gone, we've got a certain amount of time that's passed. And in this case, it's 55 seconds. And we call that the half-life because it's the time it's taken for half of the sample to decay, okay? And we can check that. If we start with 50% and we time how long it takes to get to, say, 25%, so again, this is halved, we see that the same amount of time has passed. Again, another 55 seconds has passed, giving us a total of 110 seconds. So 2 half-lives have passed now, and we've gone down by a half, and we've gone down by a half, which means that we've got a quarter left. Okay, so half times a half is a quarter. And we can check this again. If we look at about 12.5%, which again is half of 25%, we can see that this bit of the curve here, it's taken 55 seconds again, another half-life, and it's gone down by a half again, and we're left now with 1/8 of the original sample. So each time 55 seconds passes, we reduce the radioactivity by half. And that's just for this isotope. Different isotopes have different half-lives. So if I've got 2 isotopes, this one might have a half-life of 1/1,000,000th of a second. This one might have a half-life of 1,000,000 years. The half-lives can be vastly different from isotope to isotope and from element to element. And each element and each isotope of each element has a different half-life. Couple of examples here of how the numbers run. So we're going to start with 1,000,000 unstable nuclei. After 1 half-life, however long that may be for this particular isotope, we've got 500 million left. The other 500 million have emitted their radiation. They're still there, but they're no longer radioactive. They've emitted their radiation and become more stable. So after 1 half-life, we're down to 500 million. After a second half-life, we're down to 250 million. After another half-life, we're down to 125 million. And this carries on and on and on until there are none left. At some point, we'll get to around about 1,000 unstable nuclei left, and then we can continue that. After 1 half-life from 1,000, we get 500. Another half-life, we get 250. Another half-life, we get 125, and so on, until we get down to 2, and then 1, and then eventually that 1 will decay, and we're left with no radioactive nuclei. So the numbers come down relatively quickly. So start with 1,000,000, and they halve each time. So it's usually somewhere between sort of 7 to 10 half-lives. We're down to very, very few radioactive nuclei compared to what we started with, because we've divided by 2 7 to 10 times. So we're dividing by a lot there. So by the time we get 7 to 10 half-lives passing, we've basically got rid of all the radioactivity. There are 2 definitions to half-life, and unfortunately, GCSE, they love to give you one and ask you for the other. So you need to know both of these, and they are the time it takes the number of radioactive nuclei in a sample to decrease by 50%, and the time it takes the count rate from a radioisotope to decrease by 50%. And you need to know both of these so that you can regurgitate them in an exam. And you'll notice that both of these are times. Half-life is a time. Okay, so it is measured in seconds, milliseconds, microseconds, hours, minutes, days, or even millions of years. Okay, any unit of time is fair game for a half-life. Now in physics, we like to work in seconds. However, half-lives are so variable, they can literally be in any unit of time. But half-life is a time, and it will only ever be a time. Okay, so if you're asked for a half-life, you are writing down a length of time. So a bit of a deeper look at these 2 definitions now. So it's the time it takes the number of radioactive nuclei in a sample to decrease by 50%. Okay, well that's kind of like what we've looked at before. We had our 100 blue circles that turned into red circles, and the time it took for half of those to decay, that was our half-life, okay? Well, the other one's kind of related to that. If we've got 100, I'm not drawing 100, if we've got 100 blue circles, and each one of them emits radiation as it decays into a red circle, then what that means is that we saw that more decay at the start of the process. So we've got a steeper graph at the start of the process. Number of nuclei against time. More decay at the start of the process, and then fewer decay as time goes on. Well, if instead of counting how many atoms there are in our sample, we count how many of them are decaying, well, more of them are decaying at the start than there are at the end. So we can actually relabel this graph here. We would need to change the scale, but we can relabel the graph as count rate. Believe me, that says count rate, honest. We can label this as count rate. So as time passes, we see that the count rate decreases, and the pattern is exactly the same. It's this lovely sweeping curve, this characteristic half-life curve. So the two definitions are related. The time it takes the number of radioactive nuclei in the sample to decrease by 50%, and the time it takes the count rate to decrease by 50%. They are related. Okay, so we can show this on a graph. I've kind of done this already, but this is a bit more of a clearer way of doing it. Up here you can see we've got count rate, or counts per minute, decay rate, measured in counts per minute. So 20 counts per minute, 40 counts per minute, 60 counts per minute, 80 counts per minute. And if you've seen a demonstration of half-life, you might have seen a Geiger counter counting radiation and either clicking or beeping to show that it's counting. And that's what this is a measure of. And we've got time on the x-axis going up in 2-minute increments. Okay, so this is the data that's been plotted, the red curve, and we're going to look at this. Now we're going to start at 80 counts per minute. That's our count at the start of the experiment, and the half-life is the time it takes for this number to drop by half. So how long does it take to get to 40? Well, we draw two lines on a graph, and it's really important you draw these two lines here, this one and this one, because you get marks for that in the exam. We then just need to read off the axis to find out how many, in this case, minutes have passed between 80 counts per minute and 40 counts per minute. Well, 2 minutes have passed, so that must mean our half-life is equal to 2 minutes. Well, we can check, we can do the experiment again. We don't need to start again, we can start from where we're at. The counts per minute are currently 40. Should we see how long it takes to halve to 20? What are our predictions? Well, I think it's probably going to take another 2 minutes to go from 40 to 20. Let's have a quick look. Yeah, it's taken 2 more minutes. We're now at 4 minutes, so we've got 1 half-life, 2 half-lives, 2 half-lives equals 4 minutes. So 1 half-life equals 2 minutes. There's also an experiment that you can do at home to model half-life. Now, it's not perfect because we always get the same half-life, but it's a decent model for it. So if you've got access to at least 50 of something that's got 2 different sides that you can tell the difference between, such as coins, they've got heads and tails, or if you've got a big bag of Skittles or a big bag of M&Ms or something like that, where you've got an S on one side or an M on one side and nothing on the other, you can do this experiment at home. It's a good excuse to go out and buy a bag of M&Ms, in my opinion. I quite like the crispy ones. Peanut ones aren't great for this because they're not uniform enough. You need something that's a uniform shape. So a Skittle or a chocolate or a crispy M&M, perfect. Coins are also great. If you've got 50 dice, then this is a much better model of half-life, but it's not essential that you do this with dice. You can get away with something with just 2 sides. So you need at least 50 of something. More is better. You need to count how many objects you've got and record that number somewhere. Okay, now in a couple of slides time, if you're doing this in my lesson, you have a table that you can record this stuff in. What you're going to do is you are going to flip each coin, or you're going to put all the M&Ms or Skittles in a bowl, shake them up, and then tip them out onto a table, a clean one, because we want to be able to eat these at the end. There's no point buying a bag of Skittles and not eating them. What we're going to do is we'll count how many heads are up, or how many of the logos are up, so the S's or the M's. If you've got dice, you can count how many sixes there are. Although this will take you longer if you've got dice, and very few people have got dice, so it's more likely that you've got heads or Skittles. So sorry, coins or Skittles. So I will continue as if that's what you've got. So what you do is, if let's say we start with 50 coins, and we flip them, and we get 30 heads, and we get 20 tails, which is a perfectly reasonable outcome for this. You're not necessarily going to get exactly 50%. What we'll do is we record this 50. We then get rid of the 30 heads that have landed, and we count how many tails there are, and we record 20 tails. Then what we do then is this number of coins, the 20 tails, we then flip again. So this time we might get 10 heads and 10 tails. In which case what we do is we discard the heads, and we count the number of tails, and we record that in our table. We then take this number of coins, so 10 coins or Skittles or whatever we've got left, and we flip those again, and we might get 7 heads and 3 tails, in which case we're going to dispose of the heads, and we're going to record 3 tails in our table. Then we're going to flip these 3 coins again, and this time we might get 1 head and 2 tails, and we're going to record 2 in our table, and we're going to dispose of this one. And then we're going to flip these 2 coins again, and we might get 1 head and 1 tail. In which case we're going to dispose of the head. We're going to record 1 tail in our table, and we're going to flip this 1 coin, and we get a tail again. Well, that's okay. We record that in our table, 1 tail again, and we flip it again, and this time we get a head. So we discard that, and we're down to 0. Okay. So you're going to get a series of decreasing numbers in your table. What I want you to do then is, on the same slide there is a picture of some graph paper. I'd like you to plot those numbers onto that graph, and you should get the characteristic curve of half-life. And from there you should be able to work out, using our graphical method from a few slides ago, what the half-life of your coins or your Skittles or whatever are. Okay, there is the table and the graph paper. If you aren't using my Showbie presentation, then you could, I suppose, take a screen grab of that. Anyway, good luck, have fun, and I'll speak to you soon.